With the pressure time scale in determining effective and viable net zero solutions within the transport sector, it is important to understand the extent of implementing a new refueling infrastructure for an alternative fuel such as hydrogen. Today, I will be presenting research we did on multimodal hydrogen refueling infrastructure design with pipelines. My name is Krista Searle, and I'm from the Center for Sustainable Road Freight at Heriot-Watt University, and this is research that was done in collaboration with Dr. Kit Searle and Professor Philip Greening. The analysis of a strategic hydrogen refueling infrastructure, or Athena framework, has previously been developed to determine and recommend a hydrogen refueling infrastructure for effective deployment. The Athena framework introduces this three-phased approach, which looks at the demand data analysis, optimization model, and then finally an agent-based simulation model. The first two components forms part of a strategic overview where strategic decisions can be made, whereas in the agent-based simulation models, it allows for more operational decisions to be made. When we look at the demand data analysis, we look at inputs such as logistics data, data on candidate refueling sites, and then the output of this component, the demand data analysis, is a spatio-temporal mapping of the hydrogen demand. This then feeds into the second component, which is the optimization model, along with data on hydrogen production supply, hydrogen distribution, and hydrogen refueling stations. Within this component, when performing the optimization model, the output is then a hydrogen refueling infrastructure network. This may then further feed into an agent-based simulation model along with data on hydrogen refueling station operations and various uncertainties and scenarios that may be applied to look into more operational decision making. And for more details on the Athena framework, you are welcome to refer to the following article. So, in today's presentation, we're talking about research where we extended the Athena framework and applied the data analysis and optimization model of the Athena framework specifically to consider an integrated multimodal strategy that allows for the delivery of hydrogen by pipelines. And today I'll start the presentation further on with a research overview, then look into those two components, both the demand data analysis as well as the optimization model, then look into the scenario analysis that we performed, and finally conclude with some key findings. The research, called Multimodal Hydrogen Refueling Infrastructure Design with Pipelines, was conducted as part of a UKRI Strategic Innovation Fund Discovery Phase grant. It was a Northern Gas Network-led project in partnership with Heriot-Watt University, Durham University, Element Energy, Transport for the North, RISE, and Eversholt. Our scope for this research was first of all focusing on the multimodal refueling infrastructure. So we considered heavy goods vehicles or HGVs, buses, refuse collection vehicles or RCVs, and port handling equipment. Furthermore, when it comes to the hydrogen production supply, we considered both on-site or localized, as well as off-site or centralized production supply. With regards to centralized or off-site production supply of hydrogen, we need a delivery mode. And for this research, we considered both the use of tube trailers as well as pipeline. And tube trailers here looks at the gaseous form of hydrogen. And finally, this was specifically applied to a case study looking at the strategic corridors in northern England, specifically the NP11 region. All right, so focusing now on the first component of the Athena framework, which is the demand data analysis. The output from this analysis is specifically looking at a spatio-temporal mapping of the hydrogen refueling demand. And it consists of two mapping. First of all, the temporal mapping, where on the left-hand side, we focus on the overall refueling demand, identifying and determining that for each of the different modes. And from there on, we consider the different adoption and conversion rates to hydrogen in order to determine the hydrogen refueling demand for each of the modes for the different time steps. So within the temporal mapping, you identify the different time instances that you're going to consider and whether you'll consider it in an aggregated or disaggregated form. In this case, because we selected two time instances quite far apart, we considered it in a disaggregate format. From there, you move into the spatial mapping, where for each of the time instances, we can now spatially map the hydrogen refueling demand across the different modes. So looking at the application for the specific case study, first of all, we started collecting the input data specifically with respect to refueling sites for each of the different modes. Now, these are seen as candidate refueling sites. And then also the demand and logistics data. So for some of the modes, the demand was perhaps more clear as what you expect, whereas for others, such as for the heavy good vehicles, we needed to use some form of analytics to derive a certain demand based on certain logistics data. Then we selected the time instances, and for this case study, we specifically looked at a rollout phase, approximately 2027, and then a more mature phase and estimated for 2040. Then we moved on to determine the overall refueling demand per mode, and then considering adoption rates to determine the hydrogen refueling demand per mode. So for heavy good vehicles, we considered a rollout adoption of 0.1% and then a 50% adoption in the mature phase. For buses, the adoption was from 3% in the rollout to 25% in the mature phase, and for refuse collection vehicles, 1.5% in the rollout to 25% in the mature phase. For the port equipment, it was slightly different. We didn't necessarily consider a certain adoption or conversion, rather, they had a projected demand for each of these time instances. This was all done in consultation with various project partners. From the temporal mapping, we now move on to the spatial mapping. Here, we can now start distributing the demand amongst all the identified sites. And I'm not necessarily going to go into this process in this presentation, but it is documented within a paper. And then, apart from just distributing the demand amongst all the identified candidate sites, we also apply a minimum threshold to make sure that there's no candidate site with too little hydrogen demand. And how we do it is we simply say that if it is below a certain threshold, that refueling demand goes to the nearest candidate refueling site with a higher refueling demand. Looking at the output for this demand data analysis. For the rollout, on the left-hand side, you can see we have the buses denoted in little pink dots. We have heavy good vehicles denoted in green dots. The ports, the handling equipment demand denoted in blue, and refuse collection vehicle demand noted in purple. And there's also an indication in terms of the size of the demand based on the size of the dot. Then moving on to the more mature phase in 2040, the spatial temporal mapping, or the spatial mapping specifically for 2040, is noted on the right-hand side. Again, the same color legend for the different modes, and again, an indication of the size of the demand based on the size of the dot. And we can see that in the rollout phase, there's a clear distinction that the port handling equipment has a very high percentage or portion of the overall refueling demand between these modes, whereas in the more mature phase, it is clearly dominated by the heavy good vehicle demand. Moving on then from the demand data analysis to the optimization model. Within the optimization model, there are certain decision variables, meaning what we want to identify here. First is the location of each hydrogen refueling station. So a hydrogen refueling station is then when a candidate site, as identified previous in the demand data analysis, is then activated to become a hydrogen refueling station. Then for each of those activated stations, we want to know what is the capacity. For each of the stations, we also want to know what is the capacity or size of the on-site and or off-site production supply of hydrogen. And then if it uses on-site production, what is the size of the electrolyzer? If it uses off-site production, is the delivery done by tube trailer or by pipeline? And then for tube trailer deliveries, from which centralized facility is it delivered, and what is the number of daily deliveries? For pipeline, we also then recommend and look at the extension of a network. So all of these decisions are governed by the objective function, which is to minimize the cost. It consists of various portions or elements. The first is the setup and storage cost of a refueling station. Then it is the on-site setup and unit production cost, off-site unit production cost, tube trailer transportation cost, as well as the pipeline setup and unit cost. And all of this is documented within a working paper as referenced below. Finally, there's also some constraints that I'd just like to point out here. The first is that the demand from sites within a certain range may be merged, and we use a set covering approach for that. Then the aggregated demand may not exceed a certain maximum capacity for stations. All the demand in the system must be satisfied so it is met, so no demand is left behind. All station demand is satisfied by either on-site or off-site production. And if it's on-site production, we have some maximum capacities for the electrolyzers. For the tube trailers, there's a capacity of 1,000 kilogram per trip, and the tube trailer deliveries are also limited to 3 per station per day. And furthermore, it's limited to only occur within 100 kilometers of the facilities. So just some detail on the existing hydrogen pipeline assumed in the mature phase. It is noted here on the map. And again, this was in consultation with project partners. And the idea is that this would be 100% hydrogen, so there will be no blending that will occur. Right, so then we looked at some scenarios played out, where the first was for the rollout phase, having only tube trailers, and the last 3 for the mature phase with only tube trailers, mature phase with both tube trailers and pipeline, and finally having only pipeline. For the first scenario, we have the rollout phase with only tube trailers. We have 35 hydrogen refueling stations, 100% only off-site. You can see the distribution between the different modes. The centralized production facility is noted in blue, and in green we have the hydrogen filling station with off-site production supply, and the orange line denotes the tube trailer delivery taking place. Then in the second scenario, we have a mature phase with only tube trailers, 257 stations, and 1% is only on-site, 50% on-site and off-site, 49% only off-site. Here, in addition, we have in purple the stations with on-site production supply, as you can see here. What we saw here was that the system optimality is limited by the number of tube trailers deliveries per day. And you can see that in the third scenario, where we have the mature phase with both the tube trailers and pipeline, where we have 218 refueling stations, and 85% is now off-site, 14% mixed, and 1% on-site. And just for interest's sake, 32% of these stations are connected to the pipeline, and this was indeed the most cost-effective option. You'll also note here in dark blue examples of the pipeline extension. Finally, in scenario 4, we have a mature phase with only pipeline, where we have about 201 refueling stations, 100% off-site, and naturally all of them connected to the pipeline. Some of our key findings to share. Small-scale hydrogen refueling stations are most cost-effectively supplied with hydrogen via tube trailers than pipeline. And this is specifically true naturally within the rollout phase, where pipeline doesn't necessarily exist then, but also when considering on-site versus off-site. And this is specific to the model we implemented. In the second case, when we have a mature phase, the stations may develop to sizes where the tube trailers are no longer economically viable or necessarily feasible to keep up the demand, and therefore there's a need for pipeline. And what we also found was many of the optimal locations for refueling stations in Northern England are located close enough to the suggested hydrogen pipeline to cost effectively connect to this grid. Thank you very much.